In this lecture, we are going to begin implementing in Prim's algorithm. We are still in section 27, and I just went ahead and commented out all the code from the previous implementation of the minimum spanning tree. That way it's just out of the way, and we know that there's not going to be any conflicting code. So to begin this implementation, we need to bring a couple of items into scope. The first one is reverse, which I will explain when we get to there. And the next one is going to be our BTreeMap and our binary heap collections. So a lot of this should look really familiar to you because we have implemented most of this before already. So I'm just going to quickly go through setting it up. That way we don't waste too much time going over it. So we got our graph. Now we need to add in our creating our edge, and our vertex is going to again implement ord and copy, as well as our edge, ord and copy. And here we're going to pass in our graph that we want to add the edge to. It's going to be a mutable graph with our vertex and our edge generics. We have vertex 1, which is of type V, our vertex 2, and then we have our weight, which is our edge. And since this is an undirected graph, what we're going to do is go from vertex 1 to vertex 2 and from vertex 2 to vertex 1. So we want to call or and insert with, and we're going to have a BTreeMap new, which calls insert, which calls value 2 with weight. And we can copy and paste this and again reverse from vertex 1 to vertex 2. So our add edge function looks good now. So now we can add in our Prim implementation, where we're going to have our vertex implementing an ord and copy, as well as our edge. And we're going to pass in a graph, which is going to be a reference to a graph. And we need our starting vertex. And so that we have something to compare against, we are going to return a graph. That way we have a graph to test against. So now we're going to create a new mutable variable called MST, which is going to be a new graph. And we want to return our minimum spanning tree, so we can go ahead and do that. And we want to keep track of who we have visited. So we will say BinaryHeap new. And now we want to insert into our minimum spanning tree our starting value and put in a new BTreeMap. Alright, so now that we have inserted in our starting vertex into our minimum spanning tree, we now need to get all of our neighbors. So we can say for vertex with weight in our graph start, we want to push these into visited. And we're going to push them in reverse order, which I will explain why in a second. Alright, so we push in and we need to pass this in by reference. There we go. So if we look at the binary heap, we see that it says this is going to be a max heap. What reverse is going to allow us to do is it's going to allow us to take this max heap implementation and turn it into a minimum heap. And this is important because it will allow us to put all of our edges with a minimum weight first into our minimum heap. And if you remember from the previous lecture, that'll be beneficial because we want to add all the minimum edges into our minimum spanning tree first. So what we can do now, and this will help tie it all together, is while we say let sum, and then we need to reverse it, while let sum weight, and we'll say VT and prev equals visited.pop, and this is where it matters that we turned it into a minimum heap. That way when we pop off of our minimum heap, we are getting the vertex with the edge of the minimum weight, because that's what we want to check to see if it's already in the minimum spanning tree. So if it is, we can say we need to check if it's in the minimum spanning tree. So if that vertex is in the minimum spanning tree, then continue. That way we can get to the next value that we want to pop off. That way we're continuously trying to make sure that we have the minimum edge being added into our minimum spanning tree. Because if it was not already in our minimum spanning tree, well, now we're going to add it into our minimum spanning tree by saying add in our previous, connect it to our vertex, and pass in the weight. And once we add it in, well, now we need to get all the neighbors for that new vertex. So we can say for vertex weight in a reference to our graph and our vertex that we are now at, if the minimum spanning tree does not contain the key of a neighboring vertex, then we want to say visited.push, and again reverse, that way we know that it's being added in properly, of that weight, that vertex that our neighbor is at, and then our parent vertex. And that's all we have to do. So we are successfully looking at all the adjacent neighbors, getting their minimum edges, and then adding them into the minimum spanning tree, moving to that new edge that we just added into the minimum spanning tree, getting all of their edges, and performing the same logic. So our implementation looks pretty sound, so we can now test this out. And we will say config test, mod test, use super, and now we can create our test of testing our Prim's algorithm. fn test Prims. So what we need to do is create our graph. So we will say let moot graph equals BTreeMap new. And now we know that we need to add some edges, so we will say add an edge to our mutable graph. Start at vertex 0, go to 1, and our weight of 3. So we are going to create the graph that we did in the previous lecture. So we know we have 7 edges, 3, 4, 5, 6, 7. We go from 0 to 1 with a weight of 3. We go from 0 to 2 with a weight of 4. We go from 1 to 2 with a weight of 1. We go from 1 to 4 with a weight of 6. We go from 2 to 4 with a weight of 3. We go from 2 to 3 with a weight of 5. And we go from 3 to 4 with a weight of 2. So that graph is set up successfully, and now we need to create an answer graph to compare our return value to. So we will create another new BTreeMap. We know we have 4 edges here. We need to change the name of this. Change the name of this graph to ants. And we know that we go from 0 to 1 with 3. We go from 1 to 2 with a weight of 1. We go from 2 to 4 with a weight of 3. and we go from 4 to 3 with a weight of 2. 4 to 3 with a weight of 2. And now we need to assert equals that our prim and graph with a starting vertex of 0 is equal to our answer graph here. And again, this graph is what we did in the previous lecture, and this was the solution we also found in the previous lecture. So we can run cargo test, and we see that our test runs successfully. So we know that our Prim's algorithm is successfully running. So I hope you enjoyed this lecture on Prim's algorithms implementation. If you have any questions about anything that we did or on anything regarding Prim's algorithm or any other minimum spanning tree that we did in this section, please feel free to ask me in the Q&A section.